This is one of the application problems. It's problem number 1. And while it's true that I have this diagram here, the reality is we don't even need this diagram to do this problem. It's telling you in step by step what to go through. So the first thing is to express each of the vectors, the vector for the plane and the vector for the wind, in their component form. And we've been given the magnitude and the direction for each one of those vectors. So we'll start with the plane. The plane has a magnitude of 180 miles per hour. And the angle, well, because they gave us in bearings, and we see that it was north 50 degrees east, we need to find this angle here to find the angle for the vector, and that would be 40 degrees. So we have magnitude and direction. We write that as the magnitude times the cosine of the angle, the sine of the angle. Now we're going to distribute that 180, and then now all that's left here to find the components is to actually put this into the calculator. 180 cosine of 40, and then 180 sine of 40, and when you put that in the calculator, you get the component form of the vector for the plane. So now let's do the vector for the wind. The vector for the wind, well, it was given that it was 40 degrees. Actually, not 40, that says 40 degrees. I'm sorry, that should say 40 miles per hour. The magnitude is 40 miles per hour. And the angle is 0 degrees because it's blowing due east. So that would be 0 degrees. So we have the magnitude of 40 miles per hour times cosine of 0 degrees, sine of 0 degrees, and we can multiply that through, and we get that we have the component form of the wind, 40 and 0. The next part of the problem asks you to add the two vectors, their components. So I just added from the previous page that vector for the plane with the vector for the wind, and I end up getting this. So it really was just adding 40 to the A component of the plane. So we now have the resultant vector in component form. But the next part is, well, we don't want it in component form. We want to know the actual ground speed. And please read the problem when it talks a little bit about what ground speed means. The speed as it is relative to the ground. So it's like if somebody's observing the plane, this is what they see. And the magnitude would be the speed that it looks like as someone is looking at the airplane from the ground. And so we take the magnitude of this addition vector, and we get 212 miles per hour. And the other thing we need is the plane's true direction, so we use the arctangent. Since these are both positive, we don't have to do anything to the arctangent. We just plug in arctangent into our calculator, and the answer we get is the angle of the vector, which is about 33 degrees. I just rounded it to the closest degree. But in these kind of problems, we really want bearings. So if you think about it, what this is saying right here is that we have this vector with a 33-degree angle. Bearings is always looking either north or south. So since this is above the x-axis, we start off by looking north, and then we would turn to the east. And so I need to figure out what this angle is right here. But if we know this is 33, then we know that the other angle is 57, because 57 plus 33 is 90 degrees. And so therefore, the true direction, again, if someone is standing on the ground and looking up at the plane, this is what it looks like the plane is flying.